Swayam Prabha. Digital India. Educated India.
So, last class I have correlated the CSR value of cyclic simple shear to the CSR value of cyclic triaxial test. So, that means the CSR value of simple shear is alpha times the CSR value of cyclic triaxial test. Now, today I will discuss that how we can correlate this lab test data with the field data, and then how we can determine the stress developed during an earthquake. Okay. So, the field, it has been observed that the field value of tau h by sigma v dash for initial liquefaction is about 15% to 50% higher than that observed from the cyclic simple shear test. Okay, so that means we have to put some correlations between the factors, correction factors, to convert the simple shear test data to the field observed data. So, it is, we can convert in this way, the tau h sigma v dash field is equal to beta times tau h by sigma v dash simple shear. Okay. So, now this way we can correlate field data with the simple shear test data. Now, simple shear test data already been correlated with the cyclic triaxial test data. So, now I can write this is equal to alpha times into beta into half sigma d by sigma 3 dash for triaxial. So, this is a CR into half sigma d by sigma 3 dash for triaxial. So, now we can correlate the triaxial test data also with field data like this. Now, where your CR is equal to alpha into beta. Now, this from this chart, how I will get the alpha and beta? Alpha I know how to get the alpha value, because alpha expressions are available for different cases. Now, how I will get the beta value, how I will get the CR value? So, those value I can get from this chart. Okay, so from this chart you can see this is the chart. This chart is given by this Seed and Seed and Peacock. So, that their approach I am just discussing. Seed and Peacock, this reference is given. So, here suppose you will get this is the relative density RD in percentage. This is the correction factor beta in this axis, and this axis is CR. Okay, so why the beta correction factor is required? Because the field test data or field data is not same as the lab data. You can see the field value of this tau h by sigma v dash for initial liquefaction is 15 to 50% higher than that is observed from the cyclic simple shear test. So that's why this correction factor beta is applied. Beta is been applied, and alpha is the correlation factor between the simple shear test and the triaxial test CSR. Now this is the relative density. So now if this is the beta, this farm one is the beta value chart curve, and dotted one is to determine the CR value. So if I know the relative density, then I can determine the beta and CR by using this chart. Remember that this left hand side axis is for correction factor beta and right hand side axis is for correction for this CR. CR is what? CR is basically equal to alpha into beta or alpha beta. So if I know the relative density, I will get the beta and CR. Now one more thing, this test, later on I will show the chart. Those charts are developed for a particular relative density, and that relative density is 50% relative density. Now in the field, always this 50% relative density or the density of soil may be more than or less than the 50% relative density. So for that reasons, I have to again apply a corrections. So that means how I will do that for the relative density, because charts are developed for relative density 50%. So I can write that for tau h by sigma v dash field for any relative density RD2, say any relative density RD2, that is equal to your beta into tau h divided by sigma v dash simple shear into a simple shear that is for any RD1, say. So that is been RD1. So then that correction factor will be RD2 relative density divided by RD1. Okay. So that means the RD2 is the relative field relative density and RD1 is the relative density under which the tests are being conducted. So the correction factor will be RD2 divided by RD1. Similarly, this is equal to CR for half sigma d divided by sigma 3 dash for triaxial, that is again equal to, this is also triaxial RD1. Okay. So that is also RD2 divided by RD1, relative density 2 divided by 1. So this way I can determine. Now where it is tau h is what? Tau h is basically the shear stress required to cause the initial liquefaction. This is the shear stress okay, but sometimes it is the, you can see this is the your shear stress that is resistance, this shear stress amount of shear stress that is required to or this much of shear stress soil is given or resisting against the liquefaction. Okay. So now you can see that now I will discuss that how I will or here what is the RD I should write first, that RD2 is the relative density in the field and RD1 is the relative density in the lab during the test. Okay, even if you want to do your own test, there also always it may not be possible to produce or generate the same relative density as the field, then this would be your relative density you want, the relative density in the lab during the test. Okay. So now I will discuss about that how we can develop the equation for shear stress developed during an earthquake. So that is the simplified procedure. That procedure is given by Seed and Idris, 1971. So what is the procedure? Say, suppose if we take a soil column, okay. So this is a soil column. And this is the ground surface. This is my soil column. Now this is the weight of the column, W. W is the weight of the column. Of the soil column. Notice W is will be gamma into H, where H is the height of this soil column from the ground, and gamma is the unit weight. Of the soil. Okay. Now the maximum acceleration, Amax, horizontal acceleration at the ground surface, that is applied is Amax. Amax is what? It is the maximum horizontal acceleration applied at the ground surface. Remember that it is on the ground surface. Okay. So this is the maximum acceleration at the ground surface. Okay. So how much stress will be generated at this base, this depth H. So that means the horizontal acceleration is acting on the ground surface, that is Amax. Because of that, how much stress will be generated here? Tau max. How much that will be generated? Okay. That is this is stress. Now this is actually stress is gamma into H, which is your weight of the soil. Now if I divide it into G, I divided by G, so I will get the mass. Mass will be W by G. So this will be gamma H divided by G. Now this force or stress, that will be mass into acceleration. Why it will be stress? Because gamma mass is gamma into H. So that is divided by G. Now if I multiply with the acceleration, then I will get the stress, the amount of stress that is generated at this depth. It is the mass into acceleration. What is mass? Mass is gamma H divided by G, acceleration is max. So it will be gamma H divided by G into max. Clear? So that means the tau max is the maximum shear stress at a depth H due to a maximum ground surface which is max. Clear? Now this way that I am getting the tau max equal to that is that your stress is mass into acceleration, that is valid for if this column is rigid, if it is a rigid column. Now soil is not a rigid column. Soil is not a rigid body. So this mass into acceleration, that we cannot directly apply, because that can be applied if the column is a rigid column or this is a rigid body, but soil column is not a rigid column. So we have to apply a correction factor, or that is called your RD, or this correction factor you can see this is called RD, or your stress reduction coefficient. Okay. So now we will apply this correction factor. So we will write the tau max is equal to gamma H divided by G into max into RD. What is RD? RD is the stress reduction coefficient. Okay. So this is equal to stress because if your depth, if the column depth is very small, H value is very small, then this effect will not be that significant. Okay. So this effect will not be that significant. That means you will get, but as the depth will increase, now this effect, because it is not a rigid body and we are applying this equation of rigid body to this column, now this effect will be very significant. So now your stress will be very high, which is actually not the case here, because this stress, that means because of this thing, if we use the stress in this method, then as your depth increases, then we will actually get a very high amount of stress, but actually that will not exist in the reality. So that's why you have to apply a reduction factor. So that is called stress reduction coefficient. We have to reduce the stress. So that's why RD is applied, that is stress reduction coefficient. Now how I will get the RD value? So down this Seed and Idris has given this chart. So this is the range of different soil profiles for different range. This is the average line. So we will take the average line value only here. Okay. we will get this average line. So you can see this right hand side, it is depth is in meter, left hand side it is in feet. So depth is given up to 30 meter and RD is the stress reduction coefficient. I have discussed why the RD we should apply. Now here you can say up to say depth of say 3 meter or 4 meter, there is no effect actually. The RD is equal to 1. Okay, but after that you can say RD starts reducing as your depth increases and RD can reach average value can up to 0.45 or 0.5. That means the stress can be reduced by 50% at a depth of around 30 meter. Okay, so that's why we have to consider this RD. Now, next step is that our real earthquake stress versus time history if I draw the shear stress versus time history. This is my shear stress, say tau. So, and I have already discussed how we can get the shear stress at any depth in my this module 4. Okay. So, if our actual say shear stress versus time history, we may get this type of variations. Okay. So, this is my say tau max. This is the stress say tau max. This is tau max. Okay. Now, but these tests are being done for your uniform cycle. So, that means you can see here the cycles are not uniform. Actually, shear stress versus shear stress cycles are not uniform. If I draw the shear stress versus time history plot, the cycles are not uniform, but these tests are being conducted for uniform cycles. Okay, that means under sinusoidal type of loading. So, that means we have to convert these non-uniform cycles, shear stress cycle, to uniform stress cycles. For example, suppose if I draw the uniform stress cycle, so this may be the say uniform stress cycle and so on. Okay, so that means here also it can change like this. Now, how I will convert that? That is the question. So, in my previous lecture also I have discussed that it is in between 60 to your 70%. This, if we convert that. So, it is recommended that when I convert it, that uniform stress cycle, then my this shear stress, maximum shear stress in that for uniform case, it will be 65% of tau max. So, that means this value is 0.65 of tau max. Okay, that is recommended. So, now if I convert this tau max now for uniform stress cycle, okay, so I will take 65% of that. So, it is 0.65 of the tau max, and the tau max, or I should write now it is instead of tau max, I should write it is tau average, tau AV, which is 65% of tau max. This is tau AV, which is 65% of tau max. So, now tau max value is how much? Tau max is, this is the tau max value. Okay. So I can write 0.65, then A max by G into gamma H RD. Now this gamma H I can write by sigma V into RD. So where sigma V is equal to gamma into H, or that is equal to total stress. So remember that. So this is the total stress. Okay. Now here this tau AV you can write the stress developed during an earthquake. Okay. Tau AV we can write the shear stress here. So now this is the expression of tau AV. So this expression will use number of times. This is the expression that we will use, that 0.65 A max by G total stress into RD. Now how I will determine this number of equivalence stress cycle, because now we are converting that non-uniform stress cycle to uniform stress cycle. So now for different earthquake, what would be the number of uniform stress cycle? So that is important to know. So this is the equivalent number of uniform stress cycle. So that is given by Seed and Edris. So you can see this is 9, these are the equations, these are the tables. So this is Seed and Edris given in 1982, that if your earthquake magnitude is 5.25, the number of uniform stress cycle will be 2 to 3. But remember that when we are talking about the number of uniform cycles, here we have assumed that tau average is 65% of tau max. That is taken. If you change that value, then this number of uniform stress cycle will also change. But these number of uniform stress cycles are valid if tau average is 65% of tau max. Clear? So in that sense, if your 5.25 earthquake, it is 2 to 3, 6 it is 5, 7.5 it is 15 is the number of uniform stress cycle. But if you use this simplified procedure that is given by Seed and Edris 1971, you can see there they have also proposed the number of uniform stress cycle. So if I use this simplified procedure, then I have to consider this number of uniform stress cycle, because this is the way those charts are developed. Okay, and because this test has been done in the cyclic triaxial test setup, and where sinusoidal loading is applied, that's why these non-uniform stress cycles are being converted to uniform stress cycles. Now here for simplified procedure, it is mentioned that for earthquake magnitude 7, number of uniform stress cycle is 10, for 7.5 is 20, for 8 it is 30. Okay. So uniform stress cycle means what is the number of cycle of this uniform loading. Okay. So now but later on it has been modified. So it is given 1971. Now in 1982 these are the things given, where you can see in 17 was for 7.5, it was recommended for 20, but now actually later on it has been revised, and you will can for 7.5 actually it is 15. And then 1999 Idris also proposed this one, where 7.5 it is still 15. 7.7 it is 10, 7 it is 10, here also 7 it is slightly more than 10 here, but here auto 7 auto it is 10, 7.5 it is 15, 8 it is around your 22, 23, and 8.5 it is around 30. Okay, so you can see. So that's why at 7.5 actual, now we know that these are the revised table which is given for 7.5, it is 15 cycle. But if I use this simplified procedure that is proposed in 1971 by Seed and Idris, so there, if I use their chart, then I have to consider the number of equivalent circle for 7.5 as 20. But right now, after that it is been revised, now we can take the number of equivalent circle for 7.5 is 15, 8.5 is 26. Okay, here also 8.5 you can see it is now up, it is proposed 1999 because it is 71, then it is revised 82, then 1999. Okay, so here you can see it is around 8.5, it is 26 or around your 30, 31. Okay, so that means for if I compare 7.1, so 1971 recommendation for 7.5 is 20, but 1982 recommendation is 50, 1990 recommendation is around 50 also. So that means if I consider only 7.5, nowadays we will consider the 7.5, the equivalent number of equivalent stress cycle for 7.5 magnitude earthquake is 15. But if I use the simplified procedure charts, then I will consider the number of equivalent cycle for 7.5 magnitude earthquake is 20. Because that's why it is, those charts are given, and then these are recommended in that the procedure proposed by Seed and Idris 1971. Because we will use their chart later on. I will show you. Clear? Actually it is 15, but now if I use the simplified procedure, you will take it 20. Clear? But as you can see later on, it has been revised. So now these are the revised value. Okay. So now in the next class, I will solve one example problem, and then I will show you how we can apply these methods that we have discussed. So now we have discussed that how we can determine the stress developed during an earthquake and the stress required to cause the initial liquefaction. Now in the next class, I will again calculate these two stresses, and then I will show you how we can check whether liquefaction will occur or not for a particular soil. And as I mentioned, in this case, now we are discussing this is questionless your coarse grain soil, that means the sandy soil. Clear? Thank you.